Welcome to this, the first module of the workshop online tool for designing ventilation systems to reduce manure pit entry risk. In this session, what we're going to do is give you an overview of the online tool, the kind of input options that you have, and the kinds of results that you can obtain from this tool. But we'll begin by reviewing the ag safety problem that this online tool addresses. We'll give just a brief discussion of our manure pit safety program vision related to confined space manure storages. We will review the prior work that was the foundation of the development of the online tool, but then we will also discuss some of the limitations of the resulting engineering standard that was written based on that work, and then we'll introduce the online tool, we'll overview its capabilities, and then we'll give you an overview of typical results. In this session, we will not do a particular case study. That is reserved for modules 2 through 7. The ag safety problem that this addresses is a safety issue that's very critical for confined space manure storages. Confined space manure storages are those that are large enough and configured in such a way that an employee can enter and perform assigned work, such as maintaining equipment or for cleaning out or other maintenance work. And the space has limited or restricted means for entry or exit. And I think most on-farm manure storages fit that. And thirdly, according to OSHA, a confined space area is not designed for continuous employee occupancy, and I think we all agree that we wouldn't want to be in a manure pit continuously. The kinds of confined space manure storages we're addressing with this online tool are manure pits beneath slotted floor covers. They include manure pits with solid covers located outside the barn, or for manure pits beneath the animal housing barn above it. The hazards in confined space manure storages are toxic and asphyxiating gases, the most important of which are hydrogen sulfide, carbon dioxide, and ammonia. It also has the possibility of having oxygen deficient atmospheres. In some confined space manure pits, the oxygen content can be near zero. And of course, we could also have explosive gases in these manure pits. Most important of those gases would be methane. OSHA and other agencies, NIOSH in particular, defined acceptable limits for long-term exposure to manure gases. When I talk about long-term, I'm talking about an 8-hour exposure period. For hydrogen sulfide, that would be 10 parts per million. And interestingly enough, recently NIOSH has recommended that that should be as low as 1 part per million. Ammonia, the OSHA PEL or limit for long-term exposure is 50 parts per million. And interestingly enough here, OSHA has just recently recommended that this probably would be better, that it should be not higher than 35 parts per million. Carbon dioxide, 5,000 parts per million. And for methane, the lower explosive limit is 5% by volume, or 5,000 parts per million. So the problem that we have is that the fatality rate in manure pits for manure pit entry has more than doubled between 1975 and 2004. And although we don't have dozens or hundreds of fatalities per year, we do have very, very tragic accidents occurring where not only one person dies in a death event, but there are multiple fatalities. For example, a father might enter a pit to repair something and his son might be watching, or a friend or a salesperson on the farm and sees the father succumb. And then they think that I can go in and rescue that person, and they are overcome. And a third person might even go in and be overcome. So consequently, we can have multiple fatalities for one incident. Very tragic. The other thing is that exposure to entry risk is becoming more prevalent, probably because we have more manure pits in service each year. This chart demonstrates the increases in fatalities by decade. And for the decade 1975 to 84, we had 1.6 manure pit deaths per year. By the time we got to 1995-2004, it was more than doubled to 3.5 manure pit deaths per year. The trend is troubling, and this is what we're trying to overcome with our manure pit ventilation scheme. Of course, manure pit ventilation is one way to mitigate or to minimize the risk of being overcome by manure pit gases upon entry. And so it's the vision of the Ag Safety Program at Penn State that all on-farm confined space manure storage and handling facilities will have a properly designed and a properly installed ventilation system specifically configured to reduce entry risk. And this can either be a permanent installation or a temporary or a portable ventilation system. Now the work and its limitations that led up to this was conducted by a research team at Penn State University. In almost a decade-long effort, what we did is we developed and validated protocols for computational fluid dynamic simulations of gas concentration reduction and oxygen replenishment in confined space manure pits during ventilation. And we did this for a range of storages, manure pit storages with solid covers, for manure pit storages with totally slotted covers, and for manure storages with partially slotted covers. And these results were published in 6 articles. 5 of them are journal articles, and 1 of them is an international engineering safety standard. The journal articles I have listed here, the 5 journal articles I've listed for your reference, not to read them here today, but if you're interested in going back and reviewing this work, you're able to do it and access these. They're all published by ASABE, the American Society of Agricultural and Biological Engineers. The bottom publication is the ANSI/ASAB standard S607, which is an internationally recognized standard for manure pit ventilation. This standard was published and it gained consensus approval as an international engineering safety standard. You can access this standard at asabe.org, and you can obtain a copy of this from ASABE for a cost of approximately $20. The purpose of this standard, the S607 standard, was to specify, and I'm going to read this, to specify positive pressure forced air ventilation requirements, including ventilation system layout, air exchange rates, and minimum ventilation times for evacuation of contaminant gases from and replenishment of oxygen into confined space on-farm manure pits prior to entering the manure pit. Now that was a mouthful. I understand that fully, but that's the comprehensive purpose of this standard. It gives you a good overview of it. Now, the limitations of the standard are this. The recommendations that are given in a tabular format for a selected range of manure pit sizes and manure pit geometries. When you do that, you're not able to encompass 100% of those manure storages out in the field. And it's our estimation that approximately 25 to 35% of the manure tanks in the U.S. fall slightly or way outside the scope of the S607 standard. And frankly, this was one of the primary reasons why we felt that the online tool was important, because we need designers and regulatory personnel and farmers, they need access to a tool that will handle their specific situation more closely. The other thing that we needed a cost-effective way to do this. And the reason I say a cost-effective way is the simulation packages to simulate ventilation and gas decay response of ventilation systems are expensive. And if a person is only going to use this simulation software once or twice in a lifetime, it's cost prohibitive. So what we wanted to do is we wanted to be able to host the simulation software at a central location, say at Penn State University servers, and allow those occasional users to access the simulation tool through our host server. So that's what we mean by we needed a cost-effective way, for users to access this simulation tool. And then the second thing is it had to be user-friendly. It couldn't be so complex that only, a small percentage of, say, the engineers in the workforce could use this effectively. We wanted this to be user-friendly, that a wide range of facilities planners, regulatory agencies, emergency personnel would be able to use the online tool. So what is this online tool? It's a web-based computer simulation program that allows you to custom design a manure pit ventilation system and evaluate its performance. This tool can simulate ventilation of standalone manure pits. It can simulate the airflow through barns above those manure pits, and we can do that for a tunnel ventilated, a naturally ventilated, or a fan ventilated. We call it a cross-ventilated barn. In order to use this tool, you don't have to be a CFD, a computational fluid dynamics expert, and you don't even have to be an expert in the use of CAD, computer-aided design technique. We developed this tool using an commercially available CFD ventilation simulation program called SolidWorks Flow Simulation. The SolidWorks is a parametric computer-aided design software package that allows you to develop 3D CAD models of the manure storages and the barns above them, and then that's tied in with a flow simulation package, which is a computational fluid dynamics software that is fully integrated into the SolidWorks CAD programs. So what the online tool uses is SolidWorks, their CAD programming, to generate the geometry and configuration of the manure pit and barn and the ventilation system. And then it has a computational fluid dynamics, a CFD software package that allows you to simulate the airflow and the gas decay and the oxygen replenishment in both the barn and the manure pit. So it simulates the time-dependent concentration decay of hydrogen sulfide, ammonia, methane, and carbon dioxide from those barns and pits. And it also does the same thing for replenishment of oxygen in the manure pit. How does it work? You enter the airflow parameters like the air exchange rate of your fans. You input the critical dimensions of the manure pit and the barn. The online tool configures a CAD model based on your inputs. Then it's linked to this CFD simulation model. The CFD simulation is performed using your CAD model and the airflow parameters that you enter. Now what can you do with it? You can easily create a range of different configurations of manure pits and barns. You can run CFD simulations for the manure pit if it's a standalone case, or for the manure pit and the barn above it, to determine how long the pit must be ventilated to evacuate toxic gases. And also you can use the simulation to determine whether by ventilating the manure pit you develop a secondary hazardous condition inside the barn airspace. That's important to know too. So the tool is very powerful. And then it allows you, most importantly, for a given barn and pit situation, it allows you to perform a series of what-if scenarios for different manure pit ventilation system configurations. You, for example, might be interested in knowing what is the best way to ventilate this manure pit to evacuate the pit most quickly? Or how can I configure the ventilation system to minimize the portion of the barn above the pit that is contaminated during manure pit ventilation? This schematic just gives you an idea of how the online tool is configured in the computer world. You're the general user up in the left-hand corner. We at Penn State are down in the box in the bottom left corner. And the general user doesn't come to PSU's, to the ABE website site. What it does is the user accesses the SolidWorks and flow simulation work on a Penn State University server, which I call the PSU cluster with SolidWorks and flow simulation. Now the online ventilation tool, what kind of situations can you simulate? Here we show a series of figures. We'll start on the left. You can have a custom layout. For example, maybe you have a weird manure pit that has corners and little branches on it. That's called custom. Or you can have a manure pit with a T, a rectangular pit with a T coming out to the left, as I've shown here. Or it could be a very simple rectangular manure pit, or an L-shaped manure pit. The covers we can handle. You can input solid covers on this manure pit with pump out openings and access openings on it. You can have a partially slotted floor cover, or you could have a fully slotted floor cover. You can also include obstructions such as a divider wall. You can put divider walls inside this manure pit, as many manure pits do have that. You can also input other kinds of obstructions, such as in some dairy facilities, where they use sand as bedding. Sometimes sand mounds build up in those manure pits, and these are going to provide some obstruction to airflow and change the airflow patterns and the evacuation of noxious gases from those manure pits. We're able to handle that. You know, the size and the geometry is almost unlimited. Like I said, this just illustrates in the bottom right-hand corner, you know, the different kinds of floors, the different kinds of openings that you can put into these manure pits. Now, the wall openings in a standalone manure pit, you probably wouldn't have those unless you have a manure pit annex, a pump-out annex. But what it does allow one to do is if one wants to put a slot outlet or a slot in at the eave of, if you will, of the manure pit, you can do that. You can put a fan at one end where the fan is shown in the bottom right figure, and you could put an eave slot inlet right at the top of the manure pit. So you have that capability. So it's pretty flexible. The online tool, as I said before, allows us to handle tunnel ventilated barns above those pits, where in the barn we have the barn fan in one end of the manure of the barn with large ventilation inlets at the right-hand end. You see a little red dot in the floor of that manure pit, the cover of the manure pit, and that would be the pit fan. And that can be located anywhere. So the barn airflow is in the direction shown with this arrow. And we have a cross-ventilated barn above the manure pit, and you see the three black circles in the left-hand side wall, and that would represent exhaust fans for the barn. If you look carefully at this figure, you see that little red dot on the floor. That would represent the manure pit fan. Of course, we would have slot inlets to let fresh air into the barn. We have barn fans that would exhaust the air from the barn. That's for ventilation above. And of course, then we have the manure pit ventilation superimposed on that. So the barn airflow would generally, and I understand that there would be circulation and so forth, circulatory patterns, but generally the airflow pattern would be across the barn. That's why we call it cross-ventilated. And then, of course, we have naturally ventilated barns that would have open side walls, or certainly openable side walls. We'd have a ridge vent. We'd have end walls that either can be open, or they could be enclosed, or they can be partially enclosed. We'll look at that more closely in a few moments. And of course, the airflow direction of the barn ventilation would be in the direction of the wind. And I would just make a comment here. In our simulations, we assume that the wind speed is at least 5 miles per hour. We wouldn't recommend that you would ventilate the pit unless you have at least a 5 mile an hour wind direction and a wind speed, and the wind direction that we assume is assumed to be within plus or minus 45 degrees of being perpendicular to the long sidewall of the barn. Now, how do you access the online tool? We touched on this in the introductory session, but let's look at it again. You access the online tool by going to http://ventdesign.agsafety.psu.edu. Once you get there, you click, there's a button, you click on it to log in. And the first time you log in, it's going to ask you for an email address and a password that you generate, and then you would log in, and that would get you registered. Once you are registered and you access the online tool again, then you would come up with this menu where you have the opportunity to get more information about the online tool. You can create a new CFD study. You can view results. You can edit your account information, and you can also give us some feedback if you wish. If you click on Create a New Study, what it will do is it will bring up this screen, which there you see it says Pit Geometry. And on that Pit Geometry button, then what you would get is some input boxes that begin to prompt you and ask you to input data first concerning the geometrical values for the cover thickness, the length of the pit, the width of the pit, the depth of the pit, and so forth. And then as you work your way down, you would input ventilation details and so forth. I showed this screen just to give you an idea of the input format. We will look in detail at how you input a complete project in the next modules. Some of the features that are incorporated into this module: the online tool in the manure pit. You are allowed to input the location of the fan, the manure pit fan. That would certainly be at one of the, if it's a solid covered manure pit, it would be at one of the pump out locations or access ports. You're also allowed to input up to 2 outlets, air outlets. That would be access, personnel access or equipment access ports. You can include slotted flooring. You can incorporate divider walls into the manure pit in either the longitudinal or in the transverse direction. You can actually include more than one divider if you have such in your actual situation. In those divider walls, you can input up to 3 perforations, and those can either be circular or they can be rectangular, or you don't have to put any in at all for that matter. You can also incorporate pump out annexes on any one of the side walls or end walls. You can incorporate multiple pump out annexes. You can locate the manure pit ventilation fans in the top of these annexes as well. And we talked earlier that you can include obstructions such as sand mounds, or you can use the obstruction feature, to incorporate other obstructions if you wish. There's also a pit fan outlet elbow option that allows you to control the direction of the incoming airflow, ventilation airflow into the manure pit. Without the elbow, you can put the fan, into the floor of the manure pit and direct the air downward perpendicular to the manure pit cover. But alternatively, by using this outlet elbow, you can direct that airflow in any direction in the horizontal plane and any direction you desire in the vertical plane. Barn features on the tunnel ventilated barn. You can incorporate the pit fan wherever you wish in that cover. The barn fans will always be located at the left end being at the x equals 0 end of the barn. And we have openings in the end wall, opposite end wall, to represent the barn ventilation inlets. When we talk about ventilating the barns in our simulation package, the barn ventilation will always be a negative pressure ventilation system. The manure pit ventilation system will always be a positive pressure ventilation system. In the cross-ventilated barn, in the inset on the left, you can see the circles on the side end walls or on the side walls. Those represent the possible location of mechanical ventilation fans for the barn. These can be either in the end wall or the side wall. They can either be uniformly spaced along a side wall or end wall, or they can be placed in banks along the end wall or the side wall. Looking at the figure on the right, we see the fans. Here I show a fan bank in the side wall. I show uniformly spaced fans in the end wall. We have the option to include our air inlets as eave slot inlets. We can block off portions of those slot inlets if we wish. If you don't have slot inlets, for example, in some poultry facilities, for example, those air inlets would be adjustable windows. So we have the option for those kinds of air inlets in the side walls or the end walls. If you have a wider building that requires drop inlets away from the side walls, we have that option where you can use a ceiling inlet baffle and ceiling baffle openings and block-offs as well. In the naturally ventilated situation, you notice in the inset in the upper left, it shows the wind directions. We do simulations, ventilation simulations, for wind coming at an angle of plus 45 or minus 45 degrees to the long side wall of the naturally ventilated building. And as I said earlier, only for a wind speed when the wind speed is 5 miles per hour or greater. In the sketch in the center of the screen you're looking at, we show a plan view of the building, of the naturally ventilated building, and then you see around the outside some rectangular boxes that represent obstructions to natural airflow through the building, which you may or may not have in your situation. So in the naturally ventilated barn, we provide the option to input the ridge vent and its size. We can include gable sheathing alone, or we can include endwall sheathing, or we can include gable and endwall sheathing. We can also put endwall doors or other access openings in those end walls. And then we have the option of inserting or including up to 2 airflow obstructions on any one of the side walls or end walls of the building. And these obstructions, these rectangular obstructions, would represent, say, a milking parlor, or it could represent feed bins or silos, a bank of silos, or other attached buildings, or buildings that would be, or other obstructions to flow that would be within, say 10, 15 feet of the building that would still substantially obstruct airflow to the barn above the manure pit. Once you input data and you get a message that your simulation results from the online tool are prepared and ready, you would access you'll be sent an email. We'll talk about that more later in subsequent sections. And you go to the website, ventdesign.agsafety.psu.edu again, and then you would click on View the Results file, view the results, and when you get onto that, you would get a series of results files. On the bottom is a thing called Results file, specifically, and that is where you would go to get the gas decay curves and the oxygen replenishment curves. So you would click on to the file that you want to open. So if we click on to the results file, then one of these gas decay curves would appear. Like this happens to be the maximum concentration of hydrogen sulfide inside the manure storage as a function of time from the commencement of manure pit ventilation. And then on this we would have the TPEL. That is, how long did we ventilate this pit before the hydrogen sulfide concentration was less than 10 parts per million anywhere inside the manure pit. And we also provide the time to reach the more restrictive and more recent TPEL of 1 part per million, and that would take 13.9 minutes for this particular manure pit that was simulated here. And then it also has the decay curve for hydrogen sulfide inside the barn as a function of time of ventilation of the manure pit. And sure enough, for this particular building, the initial concentration in the pit was 100, and there are portions of the pit of the barn that experience concentrations greater than 100 parts per million. And it also tells how long it takes before none of the barn area, none of the barn domain has a concentration greater than 50 or greater than 20 or greater than some prescribed or desired minimum concentration inside that barn. And this is important because this would tell us that part of the barn is going to have concentrations greater than 50 parts per million hydrogen sulfide. Then we want to know how long a period of time. Well, some portions of the barn for as much as 3.8 minutes. Those portions of the barn would have to be evacuated prior to manure pit ventilation. This gas decay curve doesn't tell us which portions of the barn. It just alerts us that part of the barn needs to be evacuated. And we'll talk more about how you define which portions later on. In the results files, if you look at the bottom of the curves, you notice down below in the colored bar down below, it gives pit O2, hydrogen sulfide, ammonia, and so forth. So there's a separate tab for each gas in the manure pit or in the barn. And all you do is click on to the one that you want to look at, and you can see all the other curves. So this is a curve for the same simulation above. How long, does it take to ventilate the manure pit storage to reduce the carbon dioxide from 70,000 down to the TPEL value of 5,000. And of course it's 139 seconds in this case. Alright, so then you can go back to the overall results files, and then you notice that there's a whole bunch of animations. These are the movies. And the one I have highlighted here is for the front mid-plane hydrogen sulfide. That would be a vertical section through the longitudinal axis of the building of hydrogen sulfide concentration. The next one I clicked here is the front plane. That is at the 1/4 of the width, a vertical cross-section contour. Then there's a top plane animation of hydrogen sulfide at the midplane. That's a horizontal cross-section through the center line of at the mid-height of the manure pit. And then the one I just clicked here is an animation of the hydrogen sulfide concentration movie 6 inches above the slotted floor of this facility. And the top one that I just clicked, it gives the same information 6 inches above the floor for methane. And of course the same thing is there for carbon dioxide and ammonia and so forth. In the online tool, these movies are provided for several planes. I'm just going to show several of these. This is the front plane, which is a vertical section at the 1/4 point across the width of the manure pit and the barn. This is a front plane mid-plane. That's through the longitudinal. That's a longitudinal section, a vertical section rather, through the longitudinal axis at the mid-width of the building. Simulation results for section 3.3 would be at the mid-plane or the mid-height of the manure pit, a horizontal section. And number 4, section 4.4 would be a horizontal cross-section 6 inches above the floor. And now for those 4, here are, gives you just a taste of what the simulation results look like. The color scheme used in these is just different shades of red. You will see in modules 2, 3, 4, 5, and 6 that in the final scheme of things, these are multicolored, and we'll talk more about that later. But you get the idea that red is bad. Red is 100 parts per million. The white is 0 parts per million of hydrogen sulfide. Notice in the pit, in the sections 1.1, 2.2, and 2.2, and in section 4.4, that section 3.3 rather, that the initial color is red everywhere in the pit, and then as we ventilate that pit, it gradually turns to white. In section 3.3, which section 4.4 rather, which is 6 inches above the floor, you notice that the only portion of that pit that is totally red, deep red, is that on the left side, which would say that, well, maybe we don't have to evacuate that entire barn, but just maybe the leftmost portions. Okay, so that gives us an overview of the online tool. We didn't go into any of the nitty-gritty details of how do you input, how do you interpret results. We will do that in modules 2 through 7, and we'll begin that process in module 2, where we will discuss in detail how to input and output and interpret results for standalone manure tanks. We'll see you then.